In this video, we're going to take a look at improper integrals. An improper integral is essentially sort of a broad term that refers to integrals that deal with infinity in weird places. So normally when we integrate a function, it's a nice, continuous, well-behaved function, and we have a set of approaches that we can use to deal with those types of integrals. But what do we do if there's a discontinuity? What if there's like an asymptote in the middle of the function and we're trying to integrate through that asymptote? How do you deal with that? Or similarly, if instead of integrating from 0 to 1 with some nice constant bounds, what if you want to integrate a function all the way off to from 0 all the way to infinity? What do you do when the bounds are infinite? These are the types of questions that we're going to be answering, and it's sort of two different types of problems that we're going to be looking at. Both of them fall under this umbrella of improper integrals. So let me rephrase that all real quickly. So definite integrals, and that's what we're going to be focusing on here. Improper integrals are always definite integrals. Definite integrals, basically such as, generically speaking, the integral from a to b, some f of x dx. They need to have f of x be well defined. So they need f of x to be defined on that whole interval from a to b. And that interval is finite. Without any infinite discontinuities. When we start dealing with improper integrals, we're going to try to relax these restrictions. So improper integrals relax these restrictions. And really there's sort of two restrictions built into this that I mentioned a minute ago. One is this word right here, finite. We need our interval to be finite. One of the things we're going to relax is this idea of having a finite interval. The second one is the idea of infinite discontinuities. We are going to relax the need to have no infinite discontinuity. So basically no asymptotes. We're going to relax that possibility. So essentially right now, we're able to deal with functions that look like this. Right, here's some y equals f of x, and here's some finite interval a to b, and we can find this integral no problem. So integral from a to b of f of x in this case, dx, no problem. We can do those. We're going to take a look at now different scenarios where either our function does something and maybe it goes off like this. Let me relabel all my axes here. And what if we want a to be here and b to be way off at infinity this way? And I want to see if I can find this area. So this addresses the first point up here of having a finite interval. What if we want our interval to not be finite anymore? Or alternatively, what if we do have a finite interval, but within that interval we have an asymptote? So what if my function does something like this? And I want to go from a to b, and I want to find this area. What do we do in these cases? How do we deal with these? So these are going to be two different approaches we'll have to deal with these two different types of scenarios. Okay, and this one here is what we'll refer to as a type 1 infinite integral, and this will be what we refer to as a type 2 in just a little bit. And this is the terminology the book uses as well. Okay, so let's start with the type 1 scenario. So type 1, which I'll call an infinite integral. So let's say we consider, before we actually jump into it, let me give you sort of a scenario that'll give us some intuition for how this might behave. So let's consider a function like this, y equals 1 over x squared. And that's going to be, so this is going to be our f of x. And I want to look at the integral from 1 up to, I'll call it t, some variable. We can change the value of t to be different numbers. And I want to find the integral in this particular case. And so we can actually just do this one by hand and plug in these bounds, and it won't be too big of a deal. So in this case, if we do this integral, the integral of 1 over x squared, you can think of that as, if it's easier for you, x to the negative 2. And when we integrate it, we'll get x to the negative 1, but we'll need an extra factor of negative 1 to account for what will happen if we were to do the derivative via power rule. So the integral of 1 over x squared is actually negative 1 over x. And you can verify that either doing quotient rule, or alternatively, you could treat this as negative x to the negative 1. And if I were to take the derivative, the negative 1 would come down, make this positive, and the power would decrease by 1 from negative 1 down to negative 2, and we'd wind up with what we've got right here. So that's the idea. So that is what this looks like, and we just need to evaluate it between our lower and upper bound. And when we do that, when I plug in the upper bound, I'll get negative 1 over t, and when I plug in the lower bound, I'll get minus a negative 1 over 1. Toss some parentheses around these to make it a little more clear. So here's the upper bound minus the lower bound. This minus a negative will become positive. 1 over 1 is just 1, so this will simplify to just 1 minus 1 over t if I switch the order of these two terms to clean things up a little bit. So this is the result. And now I want to think about what happens for different values of t. So essentially what we're looking at is a picture, and let me draw this. Give you a quick sketch of 1 over x squared of our f of x that we're doing up here. It looks something like this, at least on the region that we care about. So here's x, here is y, and this f of x right here is 1 over x squared. And we're going from the point 1 up to some point t that we get to move around wherever we want. So just keep in mind right here at 1, if I were to plug in and evaluate the function at 1, when I plug in x equals 1, I'll get 1 over 1 squared, which is 1. So this height right here, incidentally, is also 1. Okay. So I'm trying to find the area under this curve to whatever value of t that we want. So if t is right here, it's not that big of an area. If t moves further this way, the area will get larger and larger and larger and so on. So let's plug in maybe a couple of ideas. So a couple of things to keep in mind. This thing extends forever off to infinity. So is the area going to go to infinity? Well, we can tell by looking at our answer that we got up here, the answer to that question is going to be no. Right? We could try to approximate this using all our little rectangles or whatever. And the idea is, if this is going to infinity, the overall width is going to infinity. But the height, you can see, is kind of going down to 0. And the question is, what is going to ultimately win? The fact that this width of our region is going off to infinity, or the fact that the height of the region is going to 0. Eventually, we're essentially multiplying 0 times infinity and trying to see who wins. Do they compromise and meet somewhere in the middle? Does the 0 win out? Does the infinity win out? If we look at the result of actually taking the integral, which we already did up here, we can see that even for really large values of t, as t gets bigger and bigger and bigger, this whole term is going to get smaller and smaller and smaller. So as t goes to infinity, for example, 1 over infinity is essentially just 0. And the whole area is going to go to 1 minus that value. So the whole area is eventually going to 1. The area is approaching 1 as t gets very, very large. And we can see that if we actually look at a pattern of individual values. So if I were to plug in and let t be equal to 2, or t be equal to 3, or t be equal to 4. What we'll see if we plug these in and we look at our areas, what is the area when t equals 2? Well, I can plug that in, right? The area corresponds to the integral. So I'll plug in t equals 2 and I'll get 1 minus a half, which is equal to 1/2. So if I put my t right here, let me erase what I had earlier. If this is the region that I'm looking at, so just this region, that area is a half. And we found that by plugging in. This height here is actually going to be 1/4 because we'd plug in x equals 2 at this point to evaluate the height of the function. When I plug in x equals 2 to our original function up here, I'll get 1 over 2 squared, goes to a height of 1/4. So this area is a half. If I plug in t equals 3, I'll get 1 minus a third, which will give me 2/3. So if I plug in t equals 4, I'll get 1 minus 1/4, which is equal to 3/4. And what we eventually can see is basically looking at a pattern of this as t gets larger and larger and larger. So I'm going to say as t approaches infinity, the area is going to be 1 over 1 minus. So the area is going to be 1 minus 1 over infinity, essentially. And for all intents and purposes, that is 0. So I'm being a little bit fast and loose here with this notation. Technically, you can't just evaluate a function at infinity. What you have to do to treat this carefully is actually take a limit. So this operation that I just kind of said, intuitively, hopefully this makes sense. I'm essentially just saying 1 over a really large number. If I let that number be large enough, it's essentially 0. I can make this as small as I want it to be by making the value of t as large as I want it to be. I can make it arbitrarily small, arbitrarily close to 0. But technically, this requires a limit. And so that's going to be our approach. We're going to involve limits. That's how we'll deal with this type of a problem. And essentially the exact way that we just did, these areas we can see are going to 1. And technically what we would do is do exactly the process we did here, and we would just toss out in front of it a limit as t goes to infinity. And that limit would carry through into all the steps, including this final step right here. And the limit would give us the answer that we were looking for. The limit would be 1. Sometimes this limit might not converge, and we'll see that. So we'll look at examples of that case as well. So let me give you, based on this intuition, let me give you some of the rules essentially that we're going to use. So again, this is our type 1, and type 1 is essentially improper integrals with infinite integration limits. Let's write it that way. Improper integrals with infinite limits of integration, or integration limits. All right. So there are a few different things that can happen, and this can look a few different ways. So let me write down a few. The first is if f is nice and continuous and well behaved, so if f is continuous on the interval from a up to infinity, and keep in mind we always have to use an open bound for infinity. You can't actually get there, so we have a inclusive endpoint on the left. We're including a, but we are excluding infinity. It's not technically a number, so just keep that in mind. Probably won't take off points for that, but just keep that idea in mind. But if this is true, then basically we're looking at a situation like this. If I want to take the integral from a off to infinity of our f of x dx, it's just going to simply be the limit as b goes to infinity of the integral from a to b of f of x dx. These two things will be equivalent. So in case 1, the infinite bound is the upper bound. In case 2, we'll look at what's if the infinite bound is the lower bound. So what if our function is instead continuous from negative infinity up to some point b? Then the same thing will hold true. We'll have the negative infinity as the lower bound, b is the upper bound, f of x dx. And same thing, we'll just take the limit as a goes to negative infinity in this case of the integral from a to b of f of x dx. And what if both bounds are infinite? So if f is continuous on all of the reals, so it's continuous everywhere on negative infinity to infinity, then the integral from negative infinity to positive infinity of f of x dx will be equal to the integral from negative infinity up to, so the way we're going to do it is basically combine these two together. We'll make an arbitrary point that'll be the upper bound of this integral, and it'll be the lower bound of this integral. We're basically just going to cut it. Cut this integral into two pieces, one that looks like the top, one that looks like the bottom. And I'm going to call that point where I'm doing the cutting C. So I'm going to integrate from negative infinity to c of f of x dx plus the integral from c up to positive infinity of f of x dx. And we're just going to pick c. I mean, we get to choose it, but pick it to be convenient. Right. Oftentimes it'll be maybe 0 is often a convenient place, but there may be a reason to put it somewhere else instead. Put that in place. And these are all true under the assumption assuming the limit exists. We will see cases where the limit doesn't exist. Basically, the limit blows up. It goes to infinity. And that tells you essentially that the area is infinite, that the integral doesn't converge to a finite number. So that's kind of the idea. In these top two, the limit exists, then if the limit exists, then the improper integral converges. And if it doesn't exist, then the improper integral diverges. And in the third, both of these integrals need to exist in order for this to be true. So all the limits have to exist, and if either of these were to diverge, then so does the whole thing. Oops, and I left off my limit. Yeah, no, we'll treat it like this. This is a fine way to write it. So I've written it like this. You would treat this piece here exactly like case 2. You would treat this piece here exactly like case 1. And so you would do limits on these two pieces separately. So keep that in mind. Okay, so again, for this integral over here, to exist, to converge, to be a finite value, these limits have to exist, and the limits implied by these, which correspond to the two previous cases. If these limits go to infinity, the integral diverges. Okay, hopefully that is clear. So let's do some examples, now that we kind of have some intuition for this. And a nice thing about this, just as a quick little preview, this idea of talking about convergence and divergence is going to be a really kind of useful idea to start to get comfortable with. We're going to be talking about this a lot later on in the semester when we get to kind of the second half of the class, right? I said the first half of the class is basically integrals. Maybe the first 2/3 of the class even is integrals. And the last portion, the last half or the last third, is going to be sequences in series, infinite sequences in series. And this idea of convergence is going to be of absolutely paramount importance when we get to that section. So it's good to start to kind of get comfortable with that idea here. Okay, so back to an example. I want to do the integral from 1 to infinity of, let's say, dx over the square root of x. And if we want to make this easier, I will rewrite this as, this is just x to the 1/2 power, but it's in the denominator, so that power has to be negative, so it's actually x to the negative 1/2 power. And we can just use now power rule on this. So this is the integral that we're dealing with, another way of writing it. And I want to evaluate it, and to do that we have to take the limit. So I'm going to take the limit as b goes to infinity of the integral from 1 to b of x to the negative 1/2 dx. If, after we take this integral and evaluate it between 1 and b, and then take the limit, if we get something that converges, that's our answer. And if it doesn't converge, if it blows up, then our answer diverges, and this integral basically also diverges. It goes, the area goes to infinity. That is the idea here. Okay, so let's take that integral, and I will get now the limit as b goes to infinity. So carry this limit in each of these steps. Don't forget to write it down until you actually evaluate it. We need to carry that limit the whole way. What is the integral of this? Well, it's going to be something with a power 1 more than this. If this is negative 1/2, the new power is going to be positive 1/2. But if I were to take the derivative of x to the 1/2, I'd get a factor of 1/2 out in front of everything that I don't want. So to account for that factor of 1/2 that I don't want, I'll put a 2 there to make up for it. And we're evaluating it between 1 and b. And so we'll plug in those bounds. Still not evaluating the limit yet, but it's going to be essentially 2 times the square root of b. If I want to rewrite it back as in a square root, you're welcome to write this as b to the 1/2 if you'd prefer, instead of using the square root, minus, and I'll just keep the 2 out of everything. We'll factor it out. When I plug in the lower bound, x to the 1/2, or 1 to the 1/2 is just going to be 1. The square root of 1 is 1. So we get something that looks like this. And again, we're now taking the limit. So here's the point that we would actually take the limit. And the first thing you do when you take a limit is just try and see if direct substitution works. So 2 times the square root of infinity minus 1 in parentheses. Well, what's the square root of infinity? It's still infinity. Infinity minus 1, still infinity. Doubling it, still infinity. This whole thing is just infinity. This diverges. And again, writing equals infinity, this is kind of, the notation here. I'm not going to worry about it. I just want you to have an understanding of the idea. But the idea is that this diverges. And this is kind of weird because I want you to think about what the graph of this looks like compared to the graph of the example we did earlier. So go on Desmos if you have a chance. Graph y equals 1 over x squared. Graph y equals 1 over square root of x, and you'll see they have the same general shape in the region that we care about. They both look kind of like this. But it turns out that one of them happens to go to 0 faster than the other one. One of them goes to 0. In fact, it's the first one. So 1 over x squared, that goes to 0 a lot faster than y equals 1 over the square root of x. And you'll see this if you plot them on the same, in fact, I should have done that. Let me do that. Let me plot these on like the same set of axes here. And again, this is just a sketch. But basically, one of them is going to go, and they're both going to go through the point 1, 1. If I plug in x equals 1 to this, to 1 over square root of 1, I will get 1. So they're both going to go through this point. And then one's going to kind of stay up higher. The other one is going to come down through the point, and it's going to go to 0 faster. And let me just try to, I guess I should do different patterns. So let's do a dashed line. So in this case, the dashed line is going to be the y equals 1 over x squared, and the solid line is y equals 1 over square root of x. They both have the same general shape, but it turns out the area of the two regions, this area, winds up being finite. It goes to 1, whereas this other area, which includes that region as well as the region kind of above it here, that area goes to infinity, which is kind of crazy when you look at it. So what I mentioned earlier, right, we're thinking of the area here as kind of being a battle between the width, which is infinity, and the height, which is going, in both cases, to 0. And the question is, who wins? Well, in one of them, the height going to 0 wins. That's in this case. This height goes to 0 faster than the width goes to infinity. And in the other case, it's the opposite. The height goes to 0 slower than the width goes to infinity. This is the kind of comparison that I want to get you guys comfortable with, and we can see that. How is the width going to go to infinity? Well, it's going linearly, right? I'm going from 1 off to just whatever x value of my choosing is. It's going like x. As you increase this, it increases linearly. But as I increase x linearly, what's happening to the other one? Well, one of them's going down to 0 quadratically, and one of them's going down to 0 like 1 over the square root of x. So it's going more slowly than linearly. And this is the battle. Essentially, if you think about it, in this case, in one case, x is going to infinity. I'm taking 1 over x squared, and I'm multiplying it by x. Right? This is the height, this is the width. In the other case, I'm doing 1 over the square root of x times x. In this case, I wind up with 1 over x. In this case, I wind up with the square root of x. What's the behavior of these two things for large x? This whole thing goes to 0. The height going to 0, 1. So keep in mind both of these are 0, both of these are infinity. We're doing zeros times infinities here, and the limit as x goes to infinity. That's kind of the idea that we're applying here. And in one case, the width loses to the height. The height goes to 0 faster than the width goes to infinity, and the overall result goes to 0. Right? So we eventually start adding no additional area, and it converges. In the other case, the height goes to 0, the width goes to infinity, but the width is going to infinity faster than the height is going to 0, and we get a result that as the limit as x goes to infinity, it diverges. This is the gist of the idea. If you can understand this, you'll understand an enormous amount of the convergence and divergence topics that we cover later this semester. So I think it's worth spending this little time on this little side tangent right here. Hopefully that makes some sense. Okay, let's do another example. So again, the conclusion of this one though was the integral diverged. It was this case down here. Okay, In the next case, let's look at this one. The integral from 1 to infinity of 1 over x dx. What is going to happen in this case? Well, hopefully you can actually tell me based on the intuition. This one looks exactly like these two other problems we did. Right? If I were to draw it, it would look very similar to these, right? 1 over x definitely looks like one of these. It's a hyperbola. It goes through the point 1, 1. But which of the two cases is going to occur? Well, in this case, you could think about it. Let me zoom back in here. So this will be a new case. I'll write it underneath this line. The height is going to 0, and I'm multiplying it by the width that's growing linearly, like x. And what is the result of this? 1. So this one went to 0 as x went to infinity. This one went to infinity as x went to infinity. And this one stays as 1 as x goes to infinity. So what happens to the overall integral? The overall integral will also diverge because you can think of this as the amount of area that we're continuing to add. So in one case, we eventually are adding 0 area onto the whole thing for each little increment. And so the whole area is clearly going to converge. It'll stop. Right? The area didn't go to 0 in that first example. The area went to 1. The idea is we're eventually adding on no additional areas. You go far enough down the line to the right, and the amount of area we're adding is negligible. It goes to 0. Whereas over here, even though the height of the area that we're adding down is going to 0, the width is growing fast enough that the width wins. And we eventually are adding things that have additional infinite area overall, and it diverges. In this case, we're adding something with finite area, but we're doing that infinitely. We're still going to keep adding another thing with an area of 1, another section with an area of 1, another section with an area of 1. The overall integral is still going to diverge because we're going to keep on adding. The further out in the x direction I go, we're going to keep on adding extra areas of 1, and the overall area is going to continue to grow to infinity. So we'll see that in just a minute. But it's kind of, this is sort of the right on the cusp. It's right on the cusp between, halfway between adding infinite amounts of area and adding 0 amounts of area eventually. We're adding a finite amount each time, and that finite amount being added repeatedly means the overall area is still continuing to grow to infinity. Hopefully that kind of makes some sense. Okay, so let's actually do this problem. This is going to be equal to the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. And what's the integral of 1 over x? That is the natural log, so I'll carry over my limit. We haven't evaluated that yet. Natural log of the absolute value of x. We're evaluating that between 1 and b. So when we plug that in, again, I'm not evaluating my limit yet. I'm going to get the natural log of the absolute value of b. Keep in mind, b is going off to infinity. These are positive values. I don't need the absolute values anymore. We can drop that if we'd like. So it's going to be the natural log of b minus the natural log of 1. What is the natural log of 1? It is 0. So keep that in mind. The natural log function looks like this. And right there is 1. The height at that point is 0. So keep that in mind. And we wind up getting, in this case, if we finally actually now evaluate the limit, so we're going to do a direct substitution, I get the natural log of infinity. And what is the natural log of infinity? It's equal to infinity. It diverges, just as I said it would. And again, that has to do with the shape of the graph. I shouldn't have erased it. As you go off further and further in the x direction, the height does indeed continue to grow to infinity. Okay. there's a couple of examples. Let's do one that will hopefully make sense in light of all these examples that we just looked at. I want to do the integral from 1 to infinity of 1 over x to the power p. So p just standing for power. What values of p allow for convergence? We just did a couple examples. We did that very first one up here. I'm really zooming out. You probably barely see it. In this first one that we did before we did it formally, it was 1 over x squared, so p was 2. Then we did, in the next example right here with the square root, p was equal to a 1/2. And then down here we did p was equal to 1. And now we're doing it generically for all possible values of p, which is going to allow for convergence. So we can do this problem the exact same way that we have been doing with the others. It's going to be equal to the limit as b goes to infinity of the integral from 1 to b of 1 over x to the p dx. So we just have to carry around this p throughout all our calculations, and it just makes things a little more confusing or a little scarier looking, but it's really not any harder than what we were just doing. So again, an easier way to think of this is maybe to write it as the integral from 1 to b of x to the negative p power dx. And we can integrate this literally just using our power rule for integration. What does that integral look like? If you have it memorized, great. Probably worth having memorized. The power will go up by 1, so it's going to be negative p plus 1 more. And then we have to divide by whatever that new, by that same power is. So divided by negative p plus 1. And we'll be evaluating it between, again, 1 and b. Notice this rule only works if p is not equal to 1. If p is equal to 1, the denominator will be 0. But if p was equal to 1, we just did that example right up here. Here's the example where p equals 1. So this requires p to not be equal to 1. But we've already seen what happens when p is equal to 1. We did that problem right here. We got the natural log out of that. Okay. So what do I get? Let me clean this up a bit. Instead of writing this as negative p plus 1, I'll start writing it as 1 minus p, just to make life a little easier. I'm going to have that limit. Haven't touched that yet. But I want to evaluate this thing at the upper and lower bound. So at the upper bound, I'm going to get b to the 1 minus p over 1 minus p. And then I'm going to subtract off the lower bound when we plug in 1. So it's going to be 1 to the 1 minus p over 1 minus p. Good. Okay, so again, I'm just plugging it in for x, b and 1 in place of the x here. Okay. What is this piece going to simplify to? Well, I'm taking 1 to the power 1 minus p. Doesn't matter what power I take 1 to, it's always going to be 1. So if we evaluate that limit, essentially what we're going to get is, let me just clean this up. Let me write this a little more cleanly, and then we'll be careful with this limit in just a minute. So I'm going to write it as b. Let's do it this way. Yeah, this will be fine. B to the 1 minus p times 1 over 1 minus p. That's just rewriting this. And then I'm going to subtract from that 1 times 1 over 1 minus p. I want to highlight the fact that they both have a factor of 1 over 1 minus p, and I'm going to be able to factor that out. And this numerator over here just simplified to 1. And so we wind up with, as our final result here, before we actually evaluate these limits, if I can clean this up a little bit, I'm going to write it as 1 over 1 minus p times b to the 1 minus p minus 1. So this is the limit. Now we actually have to evaluate that limit. So and before we do that evaluation, let's just think about it. We already said p equals 1 is off limits. That's probably a good sign that that's going to be kind of a dividing line of where behavior is going to change. So let's look at this separately with p, right, because p is not equal to 1. Let's look at this separately with p greater than 1 and with p less than 1 and see what happens in those two cases. So in the first case, if p is greater than 1, then what happens? So if p is greater than 1, whoa, there we go. Let's think about some arguments. If p is greater than 1, what happens to 1 minus p? So 1 minus p will be less than 0. So basically, if p is greater than 1, if it's 2, for example, then when I do 1 minus that value of p, I'm going to get a number that's negative. It's going to be less than 0. And what that means is that b to the 1 minus p is really b to some negative power. So if b goes to infinity and the power that it's raised to is a negative power, then we get essentially some sort of infinity to some negative power. And what happens when you take infinity to a negative power? That's the equivalent of doing 1 over infinity to the equivalent positive power. Right? A negative power is the same as doing a 1 over. And when I do infinity to a positive power, that's going to be the same as, 1 over infinity. This whole thing goes to 0. So this piece will go to 0. And what we'll wind up with, if this goes to 0, this whole thing is just negative 1. This is some other finite thing, right? We didn't pick a specific value of p, but I know p is some number greater than 1. So maybe if p is 2, this whole thing winds up being 1. If p is 3, this whole thing will wind up being negative 1/2. And then we're just multiplying by this negative number over here. We're going to get finite results. So the idea is this is the piece we were worried about. This is the piece that can make things blow up or not. If this goes to infinity when b goes to infinity, the whole thing's going to diverge. If this goes to a constant, then the whole thing will converge. And in our case, it went, in fact, not to any constant, it went to 0. So we get convergence. So again, this is the term that we're worried about. If this goes to infinity, when b goes to infinity, when we plug it in, it's the only place that b shows up. If this thing goes to infinity, that's going to be the case where we get divergence. If this thing goes to a constant, then the whole thing goes to a constant. So let's check the other case. What if p is less than 1? Then what happens? Well, now 1 minus p is going to be greater than 0. If p is less than 1, I take 1 and I subtract off that value of p, so I take 1 and I subtract off something smaller than it, I'm going to get a positive result. And that isn't just restricted. P could be positive numbers here, like 1/2, or p could even be negative numbers, and we would still get the same result. 0, -1, -2. Any of those I plug in, I will get a positive result. And that implies that when we look at this part of our, so this is the important part right here. When we look at that important part, when I look at b to the 1 minus p, it is now b to some positive power. I don't know what it is, but it's some positive power. So if b goes to infinity, then we get, following the same logic, we get infinity to some positive power. And that whole thing is just going to clearly be infinity. And that implies we are going to get divergence of our result. The whole thing, if this piece goes to infinity, the whole thing will go to infinity. And if p equals 1, so to be totally clear, if p equals 1, we did that in the last case, we already saw that the integral diverges. So now we have all of our cases. So basically, the integral from 1 to infinity of 1 over x to the p dx converges if p is greater than 1, and it diverges if p is less than or equal to 1. Okay. And hopefully this makes some intuitive sense based on that drawing that I did earlier. At least a little bit of intuitive sense. Okay, so these are the main cases that I wanted to look at here for our type 1. Let's do the other type. So again, the bounds can be finite, but the integral can have some sort of infinite discontinuity in the integrand. So, or at an endpoint of the integral or something like that. Basically, there's an asymptote somewhere within our integrand that we're trying to integrate through. So this is our type 2. And I'll refer to these as improper integrals. With infinite discontinuities. So basically with asymptotes. Let me just give you the rules for this instead of jumping into kind of the pictures. The picture is kind of similar, so let me just do a quick idea. If I am integrating over some function and it has some asymptote, right, here's some asymptote, and then the integral does something like this. And I want to go from a to b. The question is similar to the one that we had before, but kind of with the roles reversed of what's the height and the width. Now the width is clearly going to be finite, but the height can potentially go up to 0. And if we start thinking about the rectangles, right, if we start slicing it up into rectangles, eventually the rectangles that we're adding have infinite height, but again, they also are going to have, in the limit, they're going to have 0 width. And the question is what's going to win, the infinite height or the 0 width? And it's going to be the same type of question. So the height is approaching infinity for some of these rectangles. In fact, let me just clear this up a little bit. The drawing's a little too messy right now. So let's, there we go. Okay, that's better. Okay, so just think of like this rectangle. Let's just look at one of them. As I get closer and closer to that asymptote, looking at that rectangle, I want to know what its area is going to be doing. The height of that rectangle is going to infinity, but the width is going to 0, and the question is going to be who wins. So if the height wins and then that means that the overall result is that the area of this rectangle will go to infinity and our integral will diverge. But if the width wins, the 0 beats the infinity, that means that the overall area of this is going to go to 0, and we'll eventually be adding areas of 0, and we'll get a convergent result. So it's the exact same result that we had before, but instead of the height going to 0 and the width going to infinity, we've reversed the roles of those two things. So that is the idea. Okay, so let me give you the rules for this. We have 3 rules, in a sense, similar to the ones that I wrote earlier. So, and just also keep in mind, note that I drew, in this case, the asymptote occurring somewhere at the middle of the interval, in between a and b, but you could also have an asymptote literally at one of the bounds of integration, and we would have the same question, right? If I made this be the a right here instead, we're still having the asymptote, and we're still asking the exact same question we were just asking. Is this rectangles, as these rectangles get closer to and closer to this new a, are the areas going to 0 or the areas going to infinity? That's the question. Okay. Or are they going to 1, or a constant, which is a third possibility, as we saw in the case where p was equal to 1 in the previous problems. Okay, so let's just get to it. If f is continuous everywhere except for at that discontinuity, so if it's continuous on, say, a, b, with an infinite discontinuity at b, right? An infinite discontinuity is basically a fancy way of saying a vertical asymptote. Then our integral from a to b of f of x dx is going to be equal to the limit, as I'm going to introduce some new letter, we'll just call it c, as c goes to b but doesn't quite get there. So b minus, I'll call it. So a number just shy of b. The integral from a to c of f of x dx. So basically we're taking, in this case, a left-sided limit. Right, so this is in the case where our discontinuity is at the right side of our interval. So instead of going all the way there, I'll just go just to the left of it. Take a left-sided limit, just to the left of where that discontinuity occurs. And again, we'll have arguments. If this limit exists, then the integral converges. And if the limit doesn't exist, then the whole thing diverges. Or we could have the discontinuity be at the left side instead. So if f is continuous on AB, where now I'm not including A with an infinite discontinuity at A, then our integral from A to B of f of x dx is going to be equal to the limit as c goes to A plus times the integral, or of the limit of the integral from from c to b of f of x dx. So again, now in this case, our discontinuity is at the left side. So instead of having my integral go all the way to the left side, I'm going to go just to the right of it. This is a right-sided limit. Not going to quite go all the way to that asymptote. I'm going to go just short of it. Okay, so we're taking one-sided limits. And if we have a case like the one I drew up here where the asymptote's in the middle, then we're going to have to do the same thing we did before. We're going to have to combine these two types of integrals together. So let's do that third case. So if f is continuous on all of AB except at that asymptote. So except for an infinite discontinuity. At x equals c, then we'll have the integral from a to b of f of x dx, and we're going to have to split it up into two separate pieces. So we'll do it as the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And the first integral over here from a to c, we will have to treat it as one that has a discontinuity at the right side. So we'd have to treat it like the first case here. And this one, the discontinuity at the lower bound is on the left side, and we'd have to treat it like case number 2 here. So this turns it into two separate problems. And as a note, again, the integral converges if those limits exist, basically. If the integrals, or if the limits exist, basically, then we get convergence. So if they go to a constant, then we get convergence. The integral converges. But otherwise, it will diverge. Okay, so if these limits over here go to finite numbers, then the integral itself is finite, goes to that same number. But if these integrals diverge, if they go to infinity, if these limits diverge and go to infinity, then the integral also diverges. Okay, so let's do an example of this. So let's do the integral from 0 to 3 of dx over, I'm going to do the square root of 9 minus x squared. So think about this integrand, what's going on here. Well, notice when I plug in the upper bound of 3 right here, I would get 3 squared, which is 9. 9 minus 9 is 0, and I'm dividing by 0. We've got an asymptote at x equals 3. So this has a vertical asymptote at x equals 3. And you're welcome to go, again, pop this, you don't need to pop the integral in, but just the integrand. Pop in 1 over the square root of 9 minus x squared into Desmos, get a picture of the graph, and you can see what it looks like. And you'll see that sure enough, there's an asymptote at x equals 3. So the integrand goes to infinity at x equals 3. How do we actually do this problem? So what we'll do is turn it into a limit problem, take the integral, evaluate the bounds, and then apply the limit. Same thing that we were doing before. Let's say I'm going to change this to the limit as, whatever we can call it, c goes to 3 minus, so just short of 3, of the integral from 0 to c of dx over square root of 9 minus x squared. And now we can do this integral. What is this integral going to require? Hopefully you recognize this. This is going to be a trig substitution integral. So let's do our trig substitution, get some extra practice at this. Let's draw the triangle. Here's my triangle. And I need to figure out which sides are where. This side right here, the side corresponding to the 9, which I can think of as a 3 squared, it must be the longest side because it's having stuff subtracted for it for this other side that involves the square root. So that means the hypotenuse is the longest side at 3. And I'm going to put the x over here, and I'm going to put the square root of the 9 minus x squared down here. And we can, again, just verify it if you have any doubts using the Pythagorean theorem. This squared plus this squared does indeed equal this squared. Okay, this will guide our substitutions. Basically, I need to solve for x, and I also need to solve for this 1 over this square root term. So if we do that, I'll notice that, for example, the sine of theta that I've picked is going to be x over 3, which implies that x is equal to 3 sine of theta. And if x is equal to 3 sine of theta, then that means that dx, when I take the derivative, will be equal to the derivative of sine is cosine, so I'll get 3 cosine of theta d theta. So I've got my dx term. Now I want the rest of the integrand. I want the 1 over this. To get 1 over that, I want this 3 over this, and then I'll just have to multiply that by a third to account for the 3 that we've got there. So we can, or we could, however you want to do it, we could also just solve for the, yeah, let's do it that way. I'm going to just solve for this, and we'll have a 1 over cosine, as we'll see. So however you want to do it. I could either write this as a cosine or as a secant. But if I take the cosine, I will get the square root of 9 minus x squared over 3. And that implies that in this case, the square root of 9 minus x squared, which shows up in that integrand, is going to be equal to 3 cosine of theta. And I just need to put this in the denominator. I could have done it as a secant instead with the 3 on top and the square root on the bottom, and then I would have just been multiplying by a secant instead of dividing by a cosine. So again, sort of 6 of one, half a dozen of the other. Pick your poison. And so we get, when we put this all together, the integral, just zoom out so we have it all in the frame at once. The integral that I'm wanting to do is that we've got our limit of the integral from 0 up to c, and plugging in the values, our dx on top was 3 cosine of theta d theta. In the denominator, we had that square root term. Here's that square root term, so I have a 3 cosine of theta in the denominator as well. Those wind up canceling, and we are literally just integrating d theta. So this is just going to be the limit as c goes to 3 from the negative side of the integral. And I guess I should keep in mind, these bounds here are still in regards to the original x. So let me just write that. X equals 0, x equals c. So keep in mind, I haven't changed the bounds. I'm still keeping them in terms of c. We'll come back and we'll convert the whole thing to x before I evaluate the bounds. So this is x equals 0 to x equals c. But I'm just integrating d theta. And when we integrate d theta, we will get theta. So again, it's going to be the limit. C goes to 3 from the negative side of theta, evaluated again between x equals c and x equals 0. And so now we need to convert this theta back into x's so we can actually apply this evaluation. So get this in terms of x. And to do that, I will look at this line right here. If I want to solve for theta, we could do it here, but it's much uglier. I wouldn't want to use that. I would much rather use this one right here. If I want to solve for theta, I just need to take the arc sine of both sides, and we will get that this integral that we're dealing with came out to be, instead of just theta, I will write it as the inverse sine of x over 3. So that is what theta is equal to. And again, that's from this line. So this tells me that theta equals the inverse sine of x over 3 if I just take the arc sine of both sides of this. So that's what theta is equal to, and now I'm done with theta, and I can go back and not worry about having to keep writing the x next to these bounds of integration anymore, because now everything is in terms of x. Okay, so here's what the mess looks like. We will actually plug in those bounds and then take our limit. So I'm going to get, again, the limit as c approaches 3 from the left of the sine of c over 3 minus, the inverse sine clean that up. Okay, so the inverse sine of c over 3 minus the inverse sine of 0, plugging in the lower bound. What is the inverse sine of 0? So what is the angle whose sine is 0? That's how you would read this. This is the angle whose sine is 0. And sine is the y value on the unit circle. What is the angle whose y value on the unit circle corresponds to 0? That's an angle of 0. So this whole thing goes to 0. And for the other one, I'll plug in this 3 with a a number very slightly less than 3, and we will get, in this case, this limit for just this piece. So the limit as c goes to 3 just to the left of 3 is going to essentially be, we can try direct substitution and see if it works. So if I just plug in 3 itself, what will happen? So we will just get the inverse sine of 3 over 3, which is the inverse sine of 1. Again, what is the angle whose sine is 1 on the unit circle? That's pointing straight up. That's as big as you can get. This is pi over 2. You could also get that on a calculator. So what is the overall result? The answer to our original integral is this area winds up being pi over 2. Even though it's going to a vertical asymptote and the height is going to infinity there, the width is going to 0 faster. So this is a case where the battle between the height and the width, the infinity and the 0 wound up winning, and we got a convergent result. Let's do maybe one more of these examples here. Let's do the integral from 3 to 6 of 1 over square root of x minus 3 dx. I should also just point this out. I think a couple of people have noticed, but I do want to make this really clear. The examples that I pick tend to be different from the examples in the book. I'm not just working through the examples in the textbook. So if you want additional examples beyond the ones that I'm doing in these videos, crack open the textbook. Each one of those sections will have probably the same amount of examples I'm doing, but they will use different values. Occasionally I'll use the same ones. So for example, I use the same ones for a lot of these up here because I wanted to get to this question of what is the integral from 1 to infinity of 1 over x to the pth power. So a lot of these are recycled, but a lot of these other ones will be different from the ones in the book. In general, unless the book has a really, really good example that I really, really want to use, I will try to pick different examples than what the book does. So you have sort of an additional resource to go through more examples. So just keep that in mind. Okay, so what's going on here? Same issue. When x is equal to 3 in this case, this whole thing, the integrand at least, is going to infinity because the denominator is going to go to 0. I'll get 1 over 0. The whole integrand will go to infinity. So integrand goes to infinity when x is equal to 3. So we're getting an infinite height there. So what do we do? For me, going through these problems, I know I use c here, but c is such a weird number, or a placeholder for a number to use. We are so used to thinking of it as a constant. If you don't want to use c, you don't have to. You can pick another letter, because we're essentially really wanting to pick something that we kind of think of it almost as a variable when we do these limits. So I'm just going to introduce another letter that is kind of more in line with the idea of a variable in a sense. And I'm going to use t on this problem instead of c. So you can use t, you can use c, you can kind of pick whatever you're most comfortable with. So I'm going to rewrite this as the limit as, instead of c, I'm going to call it t. So as t goes to 3, but just a number just a little bit bigger than 3, because I want the number that we're going to. It's not 3 minus now, it's 3 plus, because it needs to be a number that's in the interval. So it needs to be between 3 and 6, so it has to be bigger than 3, less than 6. And I want it to be as close to 3 as possible, so that's why I picked 3 plus. This is one of those cases where our asymptote is on the left side of our interval of integration instead of on the right side. And again, I'm not going to probably do an example of one where the asymptote's in the middle. You just need to split it into 2 separate integrals. It's the same thing we've been doing, you just have to do 2 of them now. So that's why it's a little crappy. It gives you some extra work. It doubles your work. So just keep that in mind. Okay, so I'm taking that limit, and I'm going to do the integral from t to 6 now, of 1 over the square root of x minus 3 dx. How do we do this integral? Don't jump on it and say, oh, we've got to do a trig substitution, because in this case we don't need a trig substitution. If this was a square here, then yes, we'd need a trig substitution, but it's not a square. In this case, if I treat what's inside the square root as a u, I have its derivative up here, right? What's the derivative of x? It's just 1. And so I can do this one with a u substitution. So keep that in mind. So I'm going to let u be equal to x minus 3, and that means that du is just simply equal to dx. And this time we can try to choose to change these bounds to also be in terms of u, but in general I would recommend for these problems where we're dealing with the limit, I would recommend avoiding that, because every once in a while you'll get a weird change of variables that winds up like kind of almost switching which bound is above the other bound, so to speak. It can just add to a little more confusion. It can make things less intuitive. So I'm going to, again, keep my bounds here sort of as x equals 6 and x equals t, and I'm not going to convert them into u's. I'm going to leave u out of it. So I'm going to do the integration with respect to u, but then I'm going to convert back to x for actually evaluating the bounds and the limit. Okay, so with this in mind, I've got my limit as t goes to 3 plus, and I've got my bounds that, again, I'm not converting. They're still going to be in terms of x. But now this whole thing is simply du over the square root of u. And so that's just u to the negative 1/2 power. If we integrate that, I'll get my limit as t goes to 3 plus, and I'll wind up with u to the negative 1/2 will go to u to the positive 1/2. To make up for that 1/2, I'll need an extra factor of 2 out in front of everything. And again, it's evaluated between x equals t and x equals 6. And so now I need to convert back to x before I actually evaluate the bounds. So the limit as t goes to 3 plus, of 2 times u, which is x minus 3, to the 1/2. So we could write that as a square root if you'd prefer, which is totally fine. And we're now evaluating between t and 6. I can drop the x's here because now everything is clearly in terms of x anyways. Okay, so we'll evaluate, actually plug in those two endpoints. I still haven't touched the limit yet. We're just plugging in 6 and plugging in t. And so the first thing I will get is 2. I'm going to change that 1/2 power to a square root of 6 minus 3, which is going to be root 3 overall. And from that, I'm going to subtract 2 root t. So there's what that's going to look like once I've plugged in the 6 and once I've plugged in, not root t minus 3. That's what we're going to get once we plug in 6 for our upper bound, t for our lower bound. Okay, and again, this will just be root 3. It's going to be what that simplifies to. As far as this limit is concerned, when this limit hits the constant, it doesn't do anything to it. It doesn't care about this because there's no t involved. So I'm going to be able to pull that part outside of the limit. The limit doesn't care about this 2 root 3 that's sitting there, but it does care about the second part where we actually have this term. So it's going to be the limit as t goes to 3 plus of 2 root t minus 3. And now let's think about what's going to happen here. If I just plugged in t equals 3, did a direct substitution on this, we're not going to get any issues. Just a little plus sign. There we go. So if I just plug in t equals 3 directly, I'll just get the square root of 0 there, and that's totally fine. So the integrand is positive, which is nice. If this was 3 negative, we'd have trouble. If we had a number that was a little bit smaller than 3, like 2.99, and we subtracted off 3, we'd get a negative number inside the square root, and we would wind up with imaginary results. But luckily, we're dealing with numbers that are just ever so slightly larger than 3, or even 3 exactly, and that's fine. The square root of 0 is 0. The square root of a positive number exists. So this is where one of those issues could come up if we didn't think about it clearly and weren't careful with what's the plus, or where does it need to be a plus, where does it need to be a minus. So this is just going to be 0 when t equals 3. And certainly in the limit, we're good. So that whole piece goes to 0, and our end result is just 2 root 3. This is the part that survives. And so again, we get a nice converged result here. One other thing that I want to talk about, and again, this will kind of be a preview of what we're going to do when we get to sequences and series, is this all leads to an idea of what we call a comparison test. And we'll see a bunch of comparison tests later on this semester when we talk about sequences and series. And it all has to do with whether or not something is converging. But basically, a comparison test says the following. And this will be a useful concept, and it's related to what we're doing. If I've got a function that looks like this is y equals maybe f of x, and I've got some other function that can do whatever it wants as long as it stays, whoa. Here's y equals g of x, and I'm integrating from some starting point a, and I'm integrating off to my endpoint is going to be infinity somewhere over here. So I'm trying to find essentially these areas under the curves. Hopefully this is intuitively obvious. If the integral from a to infinity of f of x converges, so f of x dx converges, what will that tell me about the integral of g of x, knowing that the way I've drawn it, g of x is always less than f of x? So the idea is that g of x is always less than, let's say less than or equal to f of x. If the top area converges to something finite, so it doesn't blow up and go to infinity, then the bottom area must also converge to something finite. It can't go to infinity either. So does the integral from a to infinity of g of x dx. So that's one idea. Alternatively, what if the smaller integral on the bottom diverges? So what if the integral from a to infinity of g of x dx diverges? What if it blows up? Well, clearly the integral for the y equals f of x has to be larger than it. So if this one goes to infinity and f of x is larger, then the f of x integral also has to go to infinity. If it's the other way around, so for example, if I know that f of x diverges, it doesn't tell me anything about g of x. Just because the bigger integral went to infinity doesn't mean that the smaller integral will also have to go to infinity. So you've got to be really mindful about how you apply these. If the bigger one goes to a finite number, if the bigger one converges, then so does the smaller one has to as well. And if the smaller one diverges, then the larger one must as well. But you can't mix and match them any other combination than that. So this is kind of an idea. It relates to what we've been talking about. And this is actually going to be something that we wind up using down the line when we start talking about sequences and series. And I'll try to start working in little previews of those topics as we touch on stuff in this section that's kind of relevant to them. Because otherwise, there are a lot to handle when we eventually get there. So hopefully some of these relatively intuitive, hopefully fairly common sense ideas will give you some intuition for some of the behavior that we're going to see down the line.